In our last lesson, we explored polarization and dielectrics. We defined the polarization vector P, derived bound charge densities, and introduced the dielectric constant epsilon r and permittivity epsilon. We also established boundary conditions for D and E at dielectric interfaces. Today, we move to one of the most powerful tools in electrostatics, Poisson's and Laplace's equations. These equations let us find the electric potential V when we know only the boundary conditions, not the charge distribution everywhere. Let's derive these equations from what we already know. We start with Gauss's law in differential form. Divergence of D equals the volume charge density ρV. For a linear, isotropic, homogeneous medium, D equals epsilon E. So divergence of epsilon E equals ρV. We also know that E equals negative gradient of V. Substituting this into Gauss's law, we get divergence of negative epsilon gradient V equals ρV. If epsilon is constant throughout the region, we can pull it out. Negative epsilon times the Laplacian of V equals ρV. This gives us Poisson's equation. Laplacian of V equals negative ρV over epsilon. When there is no free charge in the region, ρV equals 0, and Poisson's equation simplifies to Laplace's equation. Laplacian of V equals 0. The Laplacian of V takes different forms in each coordinate system. In Cartesian coordinates, it is the sum of the second partial derivatives with respect to x, y, and z. In cylindrical coordinates, the Laplacian has a 1 over rho term with a rho derivative, a 1 over rho squared term with the phi derivative, and a z derivative. In spherical coordinates, it has a 1 over r squared term with an r derivative, a 1 over r squared sine theta term with the theta derivative, and a 1 over r squared sine squared theta term with the phi derivative. The general procedure to solve a boundary value problem is: Step 1. Solve Laplace's or Poisson's equation by direct integration to get V with unknown constants. Step 2. Apply boundary conditions to determine those constants. Step 3. Find E from E equals negative gradient of V. Step 4. If needed, find D, surface charge, or capacitance. Let's work through example 6.1 from Sadiku. An electrohydrodynamic pump has two parallel electrodes separated by distance d. The region between them contains a uniform charge density ρO. The left electrode is at voltage VO and the right electrode at 0 volts. Find the pressure of the pump. Given values, ρO equals 25 millicoulombs per cubic meter. VO equals 22 kilovolts. Step 1. Since ρV is not 0, we use Poisson's equation. The potential depends only on z, so the Laplacian reduces to d squared v over dz squared equals negative ρO over epsilon. Step 2. Integrate once. dv over dz equals negative ρOz over epsilon plus a constant a. Step 3. Integrate again. V equals negative ρOz squared over 2 epsilon plus az plus b. Step 4. Apply boundary conditions. At z equals 0, v equals vo, so b equals vo. That gives us b equals 22,000 volts. At z equals d, v equals 0, so 0 equals negative ρOd squared over 2 epsilon plus ad plus vo. Solving for a equals ρOd over 2 epsilon minus vo over d. Step 5. The electric field is E equals negative dv over dz. This gives E equals ρOz over epsilon minus a in the z direction. The net force on the charge is F equals the integral of ρO times E over the volume. After evaluating, the force simplifies to F equals ρO times S times VO in the z direction. The pressure is force per unit area. P equals rho O times VO. Substituting, P equals 25 times 10 to the negative 3 times 22 times 10 to the 3. This gives P equals 550 newtons per square meter. Let's summarize. Poisson's equation, Laplacian of V equals negative rho V over epsilon, applies when free charge is present. Laplace's equation, Laplacian of V equals 0, applies in charge-free regions. The solution procedure is integrate the equation, apply boundary conditions, then find E from the gradient of V. In our next lesson, we'll apply these equations to find resistance and capacitance of various geometries.